Hi, so today I'm going to be going over a board that has an issue where it doesn't power on. So this is the board right over here, and when I plug my charger in, I get no green light on my adapter, but also it doesn't turn on at all. Now, sometimes there's an issue with the charging circuit where it won't turn on, but if you plug in one of the first things I'm going to do is start measuring around main power rails. Now, on these schematics that you get, which you can find if you know how to use Google and have a brain, hint, on the first page usually there are a list of main power rails. So this is pretty much what you need in order for the computer to turn on. So I'm just going to scroll down to that over here, because a lot of this admittedly is confusing if you've never seen it for the first time. And I want to try to make it seem a little bit more simple. So you know how a desktop computer has a 12-volt rail, a 5-volt rail, a 3-volt rail, and you have it on the the yellow, the red, and the orange wires? Well, a laptop has the same general principle. So when you're using a laptop, I'm just going to turn the brightness down here so it doesn't screw with the camera too much. When you have a laptop, you have the same general idea. So you have a charger that brings 18 volts or 20 volts or 16 volts to the laptop, but at the same time you have all these other power rails that are created so that the machine can actually work. So for example, let me just zoom in so this is actually visible to you. So over here you have PP bus G3 hot, and it tells you this is supposed to be 12.8 volts. I'll zoom in a little more. Then over here you have PP bus underscore S5 underscore HS underscore computing underscore iSense 12.8 volts. PP DCN underscore G3 hot 18.5 volts. PP3V42 underscore G3 hot 3.42 volts, and so on and so forth. And then you have other rails that are dependent on specific power states of the computer. So PP5VS5, this is a rail that's supposed to be present when the computer is in S5 state or turned off. PP5VS3, this is a rail that's supposed to be present when the computer is sleeping. PP5VSO, this is a rail that's supposed to be present when the computer is on. So you can read up on what the different power states of the computer are. So for example, you have your computer on and it's open and it's running, that's SO. You close it and you see the little LED light blinking on the lid as it's sleeping, that's S3. You have the computer off, that's S5. And I may be off by 1 or 2 with the numbers, I'm honestly early and I haven't had breakfast yet, but I'm not really much of a morning person. But the point is, you have these all these different power rails, and after a while you'll just kind of get the hang of which ones you should be measuring immediately. For example, I don't care about T29 right now. For example, if you look through the circuit, you'll see that these rails are actually for DisplayPort. Now, and watch, for example, I'll just search and you'll see where it shows up in the schematic where this is. And in the beginning of what I'm doing, again, I don't care about DisplayPort. I mean, I have a computer that doesn't actually work, so why would DisplayPort matter to me? Speaking of a computer that doesn't actually work, notice how slow it is. Even with a 6-core, 3.3 gigahertz, Haswell i7, and an SSD to search through a PDF file. This is why I can't stand PDFs. So this over here is a T20, for example. This is why this is a power rail that I wouldn't check. So this is for boost regulator that pretty much powers circuitry for DisplayPort. So again, why would I care about DisplayPort when my computer doesn't even turn on? So one of the first things that I'm going to do here is I'm going to go through and check some of the basic rails. And again, you may ask me, well, how do you know where to find them? Again, board view, schematic. Where do you find board view and schematic? Google. And if at this point you ask me how to use Google, this is pretty much where I say if you don't know how to use Google, you probably should not be trying to fix motherboards, because you're going to fail terribly. So I'm going to measure around and see if my rails are present. So the first one I measure is PP bus G3 hot, because that is the main rail that's going to be creating a lot of the others. So if you don't have that one, you don't have anything else, because that 12-volt rail is responsible for many other rails in the machine. Some rails like PP3V42 are independent of PP bus G3 hot, but PP bus G3 hot is responsible for a lot of others. So if you don't have that, just get out. So I have 12.7. Schematic says 12.8. I'll live with 12.7. Next one is PP5VS3. Also notice I'm skipping directly ahead of S5, because if S3 is good, S5 should be as well. I measure and I got my 5.1 there. I'm happy. PP3V3 S5. Let's see. 3.4. PP3V3 S3. 3.4. ppbus G3 hot, no, not that, pp3v42 underscore G3 hot. At this point, I'm fairly satisfied that my power rails are present, and I'm ready to start considering other issues in the troubleshooting process. So one of the first issues that I want to troubleshoot is, why don't I have a green light? I should have a green light on this machine. I should have a green light because, my power rails are present. So if pp3v42 weren't present, which helps power the one-wire circuit, I would understand why I don't have a green light. So let's go over one of the circuits that I've talked about many times. So if this winds up being the only problem with this board, I'm actually going to label it so that I can point to it in other videos and stop re-explaining it over and over and over again. Because as you can imagine, explaining the same thing over and over again can get old very, very quickly. So let me just bring the camera up here, and we're going to start looking at the first thing that I look at when I'm having issues with the green light. So, okay, so first things first, if you're not getting a green light and the green light comes from the charger, the first thing to look at would be the charger, right? Common sense here. So over here you have the charger, and there's this line called adapter sense right over here. So right over here it says adapter sense. So what I would do with my brain is I would just try to follow this along and try to see where it goes. So it goes to this component called U6900. And then it shoots out something called sys1wire. Now the reason I know that it's shooting out sys1wire is because right over here in this little tag it says bi. The whole point is that this is a line where data shoots out and data comes back in. It's a bi-directional communication line. So this over here is going to send out a signal called sys1wire. Now this also has an input of SMC BC HAKKO VCC. This comes from this chip over here, U6901. This is a logic gate, so it pretty much, when SMC BC HAKKO comes in, it allows this 3.42 volts from here to just go right through to there, and that's about that. So this is going to get a turn-on signal. This is going to get a signal on VCC pin if SMC BC HAKKO is there. Let's see what SMC underscore BC underscore HAKKO actually does by searching through the schematic and then waiting for my PDF to load in a very slow fashion. Again, it doesn't matter how fast your computer is. 6-core i7, RAID 0 SSDs, still takes time to render a fucking PDF file. So this over here is U7000. This is the chip that I've explained in other videos, which I may link to here, controls the charging circuitry. So up there, we're talking about how to get a green light in the charger. Over here, we're talking about the charger producing voltage for the machine. So this is semi-related. So the way this works over here, and again, if you are asking how did I figure this out, I figured it out when I stupidly measured around and realized just through patterns that this does not shoot out when charger AC in is not there. The whole way this works is that the charger is over here. So you see from adapter PP DC in underscore G3 hot, it goes down to here. After it goes down to there, you have this voltage divider of R7010 and R7011. The whole point of a voltage divider is to take a higher voltage and turn it into a lower one. So you have that going to the charger AC pin. When there's 4 volts on the charger AC in pin, you will see that 3 volts gets put out on SMC BC HAKKO. So if this chip is shooting out SMC BC HAKKO, you go up. Come on. Alright. If that chip is shooting out SMC BC HAKKO, it will go to this logic gate. This logic gate will take the PP3V42 underscore G3 hot voltage coming in up here. It will shoot it out over here. And the whole way this works is that if it sees adapter sense coming over here, and it sees SMC BC HAKKO, meaning it sees that the charger is connected, so adapter sense is there, if it sees the charger is connected, and it sees SMC BC HAKKO, which means that the charging chip is happy, so if the charging chip is happy and the charger is connected, it will tell the system via sys1wire to turn on the green light. And if you see where sys1wire goes to the SMC, which is the System Management Controller, which is what pretty much controls this whole process. So the first things first, let's see what does work, what doesn't work, and what all of this stuff looks like. So we're going to look for U6901 on the board view. So you look for U6901, and the board view software says that it's right over here. So I'm going to look on the edge of my board, and I'm going to be interested in what this looks like. Let's see if that is in the area. Okay, that is the area you could see. I'm looking in this little part of the LCD, the camcorder camera, and you really just can't see shit over there. So when I look over here, let me show you what I see. So that looks like shit. See that? That looks like complete and utter dog shit. So that is the component that looks fried. So first things first is let's replace it and let's see what the traces look like. So the trace that always gets burnt on these boards is the PP3V42_G3 hot trace. So as I showed you in the schematic, you have PP3V42. Once this logic gate gets the signal, it passes the PP3V42 onto U6900. Once this chip has those two signals, so adapter sense and it has 3 volts coming in on VCC, once it has those two things, it's a happy camper, it sends out everything on sys1 wire, and it tells the green light to turn on. But if it doesn't have those two signals, it will never turn on sys1 wire, and the board will never have a green light on the charger. So let's start troubleshooting that aspect of the circuit. Now, first things first, before I even start measuring around, I can clearly see something that's broken. So since I'm staring at something that's broken right in the face, before I even bother measuring, let's start fixing. Because again, all these little parts here, like again, I buy these boards for like 15, 30 bucks when they're destroyed, depending on what type of board it is and how much is missing off of it. So I'm not really sweating it. And again, the whole idea here is to work quickly and efficiently. So it's valuable to be able to work quickly and efficiently. It's valuable to me to be able to start what I'm doing and just blaze through it. I don't want to sweat a couple of bucks here and there on parts that cost me cents. I just want to get going. That's another reason that I tell you people to not order shit off of Mouser and DigiKey. I'm not saying that Mouser and DigiKey are bad vendors. Mouser and DigiKey are excellent vendors. The problem is that, do you want to wait a week every time you want to troubleshoot something? So let's say you think the logic gate is what you need, but do you want to wait a week just to figure out that you need a logic gate? You understand? Like, do you want to wait a week just to figure out that you needed something but the 90.9 kilo ohm resistor? It's a waste of time if you have to continuously buy stuff, wait for the order to get there, and then just to figure out that there was something else all along that you actually needed. So this is a bypass capacitor, C6908. That little bypass capacitor looks like crap. And also there is the actual U6901, which itself looks like crap, and that pad looks like crap. So I'm just going to take those off. And I don't even care if that logic gate was good. Honest, I don't care. For all I know, that logic gate was good, and the only issue that I actually had here was that component itself was just, the pad on the board was just nasty. Really, it really just could have been an issue of the actual pad. Hey, come on back. So I'm scratching this pad off. Hey, long time no see.
Long time no see, D. How you been?
How are you?
Everything good?
Tired, always working. Alright, so I actually had somebody come in who I haven't spoken to in about 8 years, so I decided to turn the camera off for a second. So back to what I was doing over here. So, yeah, I don't know if the actual chip itself was bad or if it was just a trace. And since this component, when you take into account the cost of these boards, probably cost me no more than a few cents, I can't say I really care. So what I'm doing right now is I'm just going over these solder pads over here with the iron, and there's one pad in particular that's interesting to me because it's kind of destroyed. And I'm probably going to be running a wire to it. So let's just see what this looks like after a little bit of cleaning. Yeah, this looks like crap. You can tell that there's a pad right here that's scratched away, and this actually got stuck on my tweezers shoe. So let's see what we can do about that pad. We're just going to etch away a little bit at the copper on the board. So see what I'm doing here? I'm kind of trying to etch away at the copper on the board so I can make space to put some solder. See that? Now we're going to do the same over here. Now sometimes it's just totally burnt and there really is shit you can do, but sometimes it isn't. And there, so on the pad for the capacitor, the etching worked. On the other one, there's just shit that I can do. So we're going to put that new component on there. and then we're going to go from there. I like to minimize misery in troubleshooting, so I want to try to get rid of as many problems as I can at once, and that's my goal. And since this thing really is less than 17 cents to me, I can't say I care. I'm also going to try my best to not reflow the SMC, which is right next door. There's really no need to reflow the SMC if it works. That's just a nightmarish thing to do, and there's just no reason for it. Now that this is done, I'm going to plug it in. As you can see, I get a green light now. Let's see if it actually turns on with the green light, and then we can go on and continue my troubleshooting. So I get a green light, but no power on. It could be no power on, or it could just be that this testing fan that I've dropped on the floor about 90 times a day since moving this desk over here is dead. So let's try the power fan from the actual machine. Okay, so it doesn't turn on. So here, I'm going to try turning it on in SMC Bypass Mode since I at least have a green light, which requires a keyboard. So turning this on in SMC Bypass Mode means I'm going to hold down the power button on the keyboard for a few seconds, and then I'm going to plug the charger in. Unfortunately, when I do that, it still doesn't turn on. Except for now, when it actually did just turn on. Now that it's on in SMC Bypass Mode, the whole idea is it's ignoring everything that the SMC is saying to turn on. So this thing does turn on, but it turns on in SMC Bypass Mode, which means I'm going to have to replace the SMC. Most likely, it's going to be an issue with the SMC. I'm not going to include that in this video, because the SMC is a nightmare. What I'm going to have to do is I'm going to have to go through a bunch of boards that look like this, all fucked up with holes in them, and take the SMC off. Then I'm going to have to reball them with 0.25mm balls. Then I'm going to have to solder it onto this board. So I'm going to have to do BGA rework in order to fix this. But it's not BGA rework once. It's where I'm going to have to do BGA rework 2 or 3 or 4 or 5 times. Because a lot of these boards over here that get thrown away, they get thrown away because of a bad SMC. You can't just buy an SMC and put it on the board. You have to take it off of another board because it comes with programming, and it's a chip that cannot be programmed simply. So it's going to be about an hour, 2 hours of me just sitting here and cursing, doing the same thing over and over again. There's truly no reason for me to include that on camera, because that really is not beneficial to you. So, as I said, the point of this video is I wanted to make one video where I explain the one-wire circuit from beginning to end. So I'm going to go over it one more time to explain how this works. And this is a very basic explanation of it. This here is the DC jack. Pin 5 of the DC jack is adapter sense. Adapter sense goes from the charger through the DC inboard to this chip U6900. When U6900 sees 3.3 volts on pin 1 and the adapter sense signal, it sends a trigger via sys onewire, which is a bidirectional line that goes between this chip and the system management controller. Or in plain English, when this shit sees that the charger works and that the charging circuitry on the board works, it tells the SMC, hey, you're allowed to use the charger now. So, the first signal that must be present is charger sense from the adapter. The first thing that must be present is a proper adapter sense signal from the adapter, meaning you have to have a working DC inboard. So this will be different with a non-working DC inboard. You'll see something like a straight up 16 volts instead of a standard 3 volt signal. So if this is 16 volts, this usually doesn't work right, and that often happens with a bad DC inboard. If you change your DC inboard and it's still not working, you have to check this circuit. So, first things first, you need to have SMC BCA cock coming in over here. SMC BCA cock must be high. If SMC BCA cock is high, meaning this is 3.3 volts, but you still don't have a green light, look over here, and you have a good DC inboard, it's most likely an issue over here. So one of these chips is usually corroded because they're on the edge of the board, usually this one. This chip over here is attached to a main power rail of the machine. Main power rails are what go bad on the machine. Main power rails, if they send a voltage spike through it, are what are going to get damaged. So over here you have PP3V42_G3 hot. This is a main power rail connecting over here. This is a very, very common via to corrode. Also, it very often takes this chip out with it. So if you see SMC BCA cock coming in here, but it's not coming out on pin 4, check this power line. Or if this power line is here and SMC BCA cock is here, but nothing's coming out, then you have a bad chip. Again, the whole point of the circuit is sys onewire is going to tell the SMC, allow the charger to turn green, allow the light on the charger to turn green if the sense signal is present properly and there's voltage here. There will not be voltage here unless this logic gate lets this through. It's not going to let this through if it's not getting power or is screwed up in some way. If you don't have SMC BCA cock, then you need to start troubleshooting why you don't have SMC BCA cock. SMC BCA cock comes out from charger ACOC in the area of U7000. Come on, render my PDF. I give you good processing power. It's all jagged and whatnot. Charger ACOC comes out over here. Charger ACOC, which turns into SMC BCA cock, is not going to come out if this chip is fucked up, is not going to come out if this chip has a hole in it, is not going to come out if anything is wrong with this circuit. So the things that you're looking for to be correct with the circuit is charger ACN. You need 4 volts on this pin. The 4 volts on this pin are created from a voltage divider going from the adapter to R7010 and R7011. A voltage divider is going to take a higher voltage and turn it into a lower voltage. If you don't know what a voltage divider is, Google it because you're going to need to know how this works in order to repair these products. That ding also means that my next GPU replacement is ready to go. Now, if you look over here, there's also something called a current sensing circuit. I'm going to get into this in a different video. I don't want to get too much into it in this video. The whole idea behind how this works, there's going to be a voltage drop across this resistor. This chip measures the voltage drop across this resistor in order to figure out how much current the computer is actually using. So you have this resistor, R7020, coming from the charger. Then there's a 10 ohm resistor going to U7000 in the beginning of this. And then at the end of this, there's another 10 ohm resistor going to U7000. It's going to be able to tell the voltage difference between here. And by telling that, it's going to be able to tell the amount of current the system is using. I'm not going to get into the math. I'm not going to get into the formulas of how this is possible because you don't need to know any of that. And if I explain things that you don't need to know, it's just going to result in unnecessary confusion. So, let's keep it simple. If the current sensing circuitry senses the charger is taking too much power, it may not turn on the charger ACOG signal, allowing the charger to work. So the whole point of this is protection. The whole point of this is to see how much power is the charger using. So if something's wrong here, or one of these resistors is out of whack, and it causes the U7000 to think that the charger is using 9,000 amps, it's obviously going to turn off the charger, meaning it's going to turn off this charger ACOG signal. So if you don't have SMC-BC ACOG, if you don't have SMC-BC ACOG over here, check the U7000 area. If you do have SMC-BC ACOG here, then you have to check this area to see what's wrong. And again, this really is just following the numbers, following the lines to figure out the issues. This is a very, very common issue because this is they have the smallest via going to the smallest logic gate right on the edge of the board. It loves to get fucked up by water, and it is a very, very common fault. So again, I am going to be going down a rabbit hole with this board to make it work again, but I did solve what I set out to show you in this video, which is that how to fix and how to troubleshoot one-wire circuit issues. And that's about it for today.